All right. I'm going to work through this worksheet since the recording isn't working. So for this problem, we suspect women administrators earn less than men at a local hospital. Records indicate men earn an average of $85,000 a year with a standard deviation of 10,000. A random sample of 25 women administrators was taken and the sample mean was 82.9. Perform a hypothesis test to see if there's evidence to claim women earn less. They say alpha is 0.05. Alpha is your significance level. So your significance level is 0.05. Your null, H0, H naught, is that the average salary of women is exactly the same as the average salary of men. Your alternative, what you're trying to prove, is that the average salary is less than what men earn on average. So your test statistic, I'm going to give you the formula once. It's your x bar minus your mu naught over sigma over square root of n. But I'm going to show you how to use your calculator. So 82.9 minus 85 over 10 divided by square root of 25. This works out to be minus 1.05. And so the p-value, once again, I will show you how to do that using your calculator, is 14.69. And so this will be the sampling distribution that goes with it. Oh, my picture. Oh, let me see if I can do a better picture than that. That's kind of yicky. So this is my normal curve. My test statistic is minus 1.05. And since my alternative hypothesis is less than, I want to shade the left tail. So that's the probability we found. And this particular probability is 1469. So based on your p-value, will you reject or fail to reject? Well, the p-value is greater than our significance level. 14.69 is greater than 0.05, so we're going to fail to reject the null. And if we fail to reject the null, that means we don't have evidence. We have insufficient evidence to say women earn less than men on average. Remember, very low p-values, less than our significance level, gives us evidence that the alternative is what's really going on. So that's the first example. Let me show you how you would do this using your calculator. So what you would do is, I have a screenshot. You need your calculator. You want to hit the stat button. So this button right there. And when you hit that, you end up seeing this, and then you want the tests. You want to click tests. And when you click the tests, you see this screen. And you want to hit the z-test. So when you click on this, the z-test, you're going to see this one. And this is where you're going to enter all your information. The null hypothesis is that the mean is 85. So the mean is 85. There's your mu naught. Population standard deviation is 10. You were told that standard deviation was 10. Your sample mean was 82.9. That's your x bar. You had 25 in your sample. There's your test statistic, minus 1.05. That was from using this formula. That p-value of 1.1469. 0.1469. Notice we had to select this less than because of this less than. So that's this example. Let me do a second example. So this one here, we have a college professor, is to see if their new teaching method improves test scores. In the past, the students had a mean test score of 71.3. So that's what we're going to compare to. The old mean. we're trying to test that the mean now is improves test score. So if it improves, that means we think the test score is going to go up. So in this, we have our sample mean was 75.1, population standard deviation was 12.1, and you were told n is 40. So for this one, your z-score ends up being 1.99 when you plug all them into the formula, and you get a p-value of 0.0235. Using technology, we're going to get both this and this. Let's draw the curve that goes with it. So my test statistic is 1.99. So the shaded region is this because my alternative is greater than. So I'm using the right tail. So this area is 0.0235. That is a low p-value. This is less than our significance level of 0.05. Since it's a low p-value, we are going to reject the null. Our null is very unlikely. So we have evidence for our alternative. We have evidence that the mean test scores improved. You could also say are greater than 71.3. The whole purpose of this was to see that if this new teaching method made test scores go up, because we want to know if we continue. So this is giving us evidence that they do. Once again, let's go to technology. So let's find that one. So we would get to this screen like we did before. You can go back and look it up again, the buttons to get to it. As you can see, oops, wrong one. Let me find it. There it is. There's the right one. So do you see the mean is 71.3, the standard deviation is 12.1, the sample average was 75.1, the sample size was 40. There's my test statistic. I just rounded it to 2 decimals, 1.99. My p-value was 0.0235. This is the shaded region. It's almost 2 standard deviations above. So this is how I can get the answer for my test statistic and the p-value using technology. Let me do the last one. Do students sleep a different length of time? This time we want to use a significance level of 0.01. So if students are no different, then the San Francisco State average sleep would be the same as a typical. We're testing to see if it's different. So this is not equal. We're not specifying higher or lower. My sample results were 5.9. I'm told the standard deviation is 1.2, and I sampled 9 students. So my test statistic ends up being minus 2.8. That's a really low or that's very far away from the mean. That's almost 3 standard deviations below. So this is going to be a very low p-value. 0.0051 is my p-value. Let me sketch the curve that goes with it. So minus 2.80. Now notice this is a not equals. So because it's not equals, I have to do a two-tail. So I've gone minus 2.8 this way, so I've got to go plus 2.8 this way. And so my p-value is these 2 shaded regions. So those 2 shaded regions add up to 0.0051. So this is a very small p-value. It's much less than my significance, so I am going to reject that null. So if I reject the null, I'm going to say I have evidence for my alternative. So we have evidence that the average number of hours SFSU students sleep is different from 7.02, or you could also say different from a typical or the national average. So those are the different ones we want. And